All right, 8 o'clock. Welcome back to your favorite class. Roar! Today, the topic will be woven composites. I was debating how much time I should spend. I'm going to try to get through this quickly. All right, like 1 day, 1.5 day on woven composites. I feel like it would be an absolute injustice if I didn't talk about woven composites to you guys because they're so commonly used. And if you went into industry and didn't know what a woven composite was and didn't know words like warp and weft, then it would be anarchy and people would be like, "What? You didn't learn anything about woven composites? What's going on? You're crazy." Okay, so we got to talk about woven composites. And the math behind it is very similar, so we're not going to talk too much about the analysis methods, but you just need to come away from this class with nomenclature about woven composites and some general knowledge about like what they are and how they're made and what the current state of affairs is for woven composites. So that's what we're doing this week. Really want to try to get like 1 or 1.5 days in it, and then the rest of the time sandwich composites. All right, then your exam. You only got 2 weeks left. 2 weeks. That's it. And then this lecturing behind the wall is over, hopefully, not continuing into the fall. Okay, so I haven't posted the homework on this woven composites yet. I don't exactly know what to ask you about. It's really like qualitative stuff, but I'll figure something out. Okay. So we got one more homework that'll be on woven composites and sandwich structures, and then your final exam next Friday. I will put an exam study guide out for you probably later in the week this week. All right, so look for that as well. Without further ado, I posted new notes to Blackboard on woven composites. Take a look at that, and then let's get going on woven composites. How's my meme today? I feel like that's very commonplace where professor's explaining something to someone and you're just like trying to listen from afar. You like cup your ear, like behind your ear, trying to make like a radar system out of it. Yeah, very common. All right, let's get my notes here. All right, topic today, woven composites. I particularly like the first slide of the slide deck this particular go around. It's got some cool pictures and sort of introduces the topic in kind of a general sense. So I'm just going to pull one picture in here and just talk about this quickly. And I'll give it kind of a baseline for what I mean by woven composites. Like most of what we talked about in this class has been unidirectional composites. And so woven composites are those where like the fabric before presentation is arranged in some pattern that's not like a unidirectional pattern. Okay, so this picture like tells a pretty good story about what would be a three-dimensionally woven composite system. Where here, like this blue is like a toe, so thousands and thousands of individual fibers, just kind of like woven in between this sort of like wave fashion between what are straight warp and weft toes, right? So you got some toes that are going this direction and some toes that are like going this direction. These are warp and weft toes, and we'll talk about that in just a minute. And so here's like what I would consider a fabric unit cell of like a three-dimensionally woven fabric. All right, and from this you can make a composite. And if you're kind of looking at it from a top, without any load on it, you might see something like this. Okay, where now if you're looking at it from the top, you start to see some of these things. Like here, this blue, what we call a Z toe, the through thickness toe. You can sort of see in the manufacturing after the composite. This is a view from the top. You can see that Z toe kind of going over two of these toes that are running in sort of this parallel direction. This horizontal direction, you can sort of see these Z toes from above. Now, what happens when you like load something like that is some crazy sorts of stuff and some crazy damage that might occur. So, for this reason, 3D woven composites are a little suspect because they have this Z-toe, which can really muck things up. So if you like end up loading this guy this way, you see all this like cracking that occurs. It's just like really horrible. You know, we've talked about what happens when you load unidirectional composite in the 90-degree orientation. That's kind of like what's happening here. And so you see all these like cracks that form and it's really like nasty looking stuff. And you can also kind of load it the other way and you'll get cracks that sort of form the other way. So generally you can see that woven composites, we will see that they have very good like fracture resistance because they have this through thickness toe coming through, but their in-plane properties are not the best. Okay, so this is what happens if we're going to load the other direction, kind of along the same direction as these Z toes, as these woven through thickness toes, right? So either way, some like extreme damage, some crazy transverse cracking that's going to cause ultimate failure, and some loss of in-plane properties with these woven structures, but generally you gain a lot of fracture toughness benefit. Okay, so that's kind of our little introduction. There is like some nice cool pictures that I wanted to show. All right, so let's dive in and have a little bit more technical definition, and let's get our vocabulary going. All right, so here we go with fabric architectures. And I would say that woven composites are composites that are made from fabric architectures that were not one-dimensional. So let's talk quickly about these fabric architectures. All right, so fabric architectures are commonly categorized by dimensionality of fiber travel. All right, so you'll see like 1D, 2D, or 3D. Obviously, a 1D composite is made from unidirectional fabric. And so this is what we've basically talked about the entire time in this class. It's how we construct laminated composites, and it's what our analysis has mostly been on. So here's like your unidirectional composite, where you got fibers all running just in one dimension. All right, so here we go. It's one dimension that these fibers travel in. All right, so that's a unidirectional. If you make just a unidirectional composite, it would not be considered a woven composite. Even if you stacked a bunch of unidirectional layers on top of each other, not a woven composite, because it's not made with architectures that are higher than one-dimensional. So these are your 1D unidirectional architectures. Your 2D architectures are those that have fibers sort of moving in more than one direction. So usually it's like an in-plane sort of fabric. All right. And so some names that you might see here. Looks like I have a question. Do I have a question? A plus 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 plus. Okay, that's Justin. That must be in response to my meme. Or maybe he just really likes my pictures. I don't know. Unclear. All right, 2D composites. You are probably most familiar with like a plain weave or a satin weave or a twill weave, which is a specific type of two-dimensional fabric, but there are other types. So we would generally classify those types of weaves as bidirectional weaves. And so that's like your plain weave, twill weave, satin weave, etc. All right. So those bidirectional weaves, those are things that you've sort of seen in the past. I introduced those in 429, and we talk about those in 429. I think I had you identify them on an exam. So those things you know. There are other types of 2D fabrics, like knitted fabrics. So think of like clothing manufacture. All right, like these clothing that I have, it was made in some way on some loom. All right, so is this a plain weave? Is this a twill weave? Is this a knitted fabric? Is this a stitched fabric? Okay, these are the things that make up the backbones of what could be two-dimensional composites. All right, knitted fabrics. There's braided fabrics, and you can also have continuous strand mats. All right. So continuous strand mats are just like you have a bunch of fibers and you just lay them down in a mat, and they're all just like randomly oriented in a plane. All right. Now let's get a picture in here and show what these guys kind of look like. So most of these you have sort of seen before, but maybe some of these you have not. So the pictures here will be helpful. Pictures worth exactly 1,000 words. Exactly. I counted. Why did it go way down there? What the hell? Technology sometimes, you know. Okay. So here are some of your 2D architectures. All right, and as I mentioned, there's like this bi-directional weave, which sort of looks like this. Here's an example of a plain weave bi-directional. You can have multi-directional, though this is very uncommon because it's actually difficult to manufacture something like that. You can have weft knitted, so we'll talk about weft and warp in just a second. But this sort of knitting structure, uh, what is it? Stitch and purl. You guys, anyone doing any knitting out there? Stitch to purl to. All right, so you can do weft knitted, warp knitted. Braiding we'll talk about, useful for making cylindrical structures, and you can have bidirectional or tridirectional braiding. These are probably equivalently difficult to manufacture or easy to manufacture, however you kind of look at it. All right, so these are your kind of types of two-dimensional fabrics where the fibers are sort of contained just in one sort of plane. And then the next dimensionality up would be three-dimensional fabrics. And 3D architectures can be made in a variety of different ways. Back in like the 70s, they were doing this Z pinning and stitching that I kind of mentioned before, and that's like a quasi 3D. And so I sort of put this here with quotation marks, but here I'll say stitched and pinned. (2D fabrics). Okay, I put this in quotation marks because if you just have a two-dimensional fabric and you put a bunch of stitches into it, like the through thickness dimension, like, is that really a 3D composite? I mean, you're kind of like cheating. I guess you're incorporating like fibers through the thickness, but it's not really part of the manufacturing process. So I don't like it much, but technically it is like a three-dimensional woven structure because you do have a fiber going through the thickness. So, technically yes, but it's like asterisk. Okay, it's like it took steroids and it's trying to get into the Hall of Fame. All right, it's cheating. All right. So stitched and pinned 2D fabrics, but much more on par would be like an orthogonal weave, or sometimes what's called an X weave. Those are very common types of three-dimensional woven structures. And so let's take a look at what those might look like. And so here are your three-dimensional architectures. And so that very first unit cell that I showed at the very beginning of lecture was this 3D orthogonal weave, right? Where you've got like toes that are coming across the plane, so that would be like these guys here, toes that are going into and out of the plane, which would kind of be like these, like what we signify as like these black guys here, I think. And then you've got these through thickness toes, which are kind of like woven over and under, kind of interlocked throughout those cross and those across and in front toes as well. All right, so that's a 3D orthogonal weave. Very difficult to manufacture that, but probably the best three-dimensional composite that you could make. All right, these are some other types that you could see. This is a angle interlock weave. That's not truly three-dimensional. It's kind of, again, kind of this quotation marks, I'll say. The 3X weave, yeah, that's three-dimensional. And then this 3X weave with warp fill. So very, very similar there in that you have these crazy kind of weave patterns. All right, so I want to talk about each one of these in kind of gory detail and talk about the benefits and drawbacks of each. And we'll talk about how these fabrics are manufactured and what benefits and drawbacks you'll get from each and what the knockdowns or reduction in each of these general properties kind of would be. All right. So categorized by architecture. We'll start with unidirectional just to kind of kick things off, but we've talked about unidirectional since like the beginning of 429. So you've seen like 18 weeks of instruction of unidirectional composites. Like, I don't know how much more you really need to see on unidirectional at this point. Like, hopefully you're kind of getting it. All right. So unidirectional, which is like 1D composites. So the general picture you should have in your head is, you want to make a laminate, you have one-dimensional composite, and so the picture you should have in your head is again something that looks like this, right? Where you've got this unidirectional fabric, and it is feeding into these individual layers that make up what is like a laminate stack, and you can arrange them in a certain character so that you build them, build them, build them, build them, build them, and to make the composite that you want. Okay, so a cross section might look something like this after you've done this manufacture. All right, and this has voids in it, but don't mind the voids. The idea here is that you're stacking this up, and you have 0 degree, 45, minus 45, 90 degree layers, and you're making this laminate stack. Now, this is not a woven structure because the layers are not like interlocked with each other, right? So this is not a woven structure. All right, and that's because there's no 2D interlocked architecture. All right, so there you go with unidirectional. And we know that unidirectional materials, the way that they're manufactured is pretty straightforward. You get all these individual toes from a creel, they come together, and they're either going through the solvent impregnation or the hot melt pre-pregging process, usually to make pre-preg. Otherwise, they can come in dry fabric, and the manufacturing there is pretty straightforward. I didn't feel the need to talk too much about the manufacturing here, but I'll say here that unidirectional fabric comes most often as pre-preg. So that's like 90% of the time it's coming as pre-preg. So you can get unidirectional fabric in dry form, but it's not all that great, not all that common. You have to stack many layers on top of each other to get what you're trying to do. So most of the time, unidirectional fabrics are coming as pre-pregs. All right. And then the most common manufacturer of composites from those pre-pregs is autoclave or out of autoclave vacuum bagging. There's that OOA again. I talked about that in 429. This is out of autoclave vacuum bagging. All right, so if you don't got an autoclave, all you can do is like put it inside of a bag and pull vacuum on it to do your best to try to swage everything down and kind of get as much pressure as you can. All right, so I'd say those are the kind of the most common manufacturing methods for the unidirectional or one directional fabric styles. All right, I just want to bring in a data sheet here because let's look at what the data sheets actually look like for unidirectional composite, because we'll compare to like 2D and 3D woven composites in just a second. All right, so a data sheet. Here, this is this is the same unidirectional material that I used when I created the laminate in day number 2, way back in February, I think that was. God damn, that's a long time ago. Remember that way back when I made that composite? Yeah. This is the pre-preg that I used. Okay, so a couple things I want to point out here. It tells you like the amount of fibers in each toe. There's 12,000 fibers in each fabric toe. Here, this is a carbon fiber pre-preg. Woven pattern here, we see non-woven, okay, because it's a unidirectional pattern, so that's of interest. And here, this fabric aerial weight. I've kind of alluded to this before, but I want to just draw this directly because I don't think I've made a very specific point about aerial weight. And the idea here is how much does one aerial unit weigh? Okay, so if you've got a fabric that's, looks like this, and it's got 1 yard by 1 yard dimension, okay, it has a area of 1 yard squared. All right, so this fabric aerial weight here, 4.3 ounces per square yard. It's a very common metric that you'll see for composites, because the indication of the weight per square area gives you an idea of how dense the fabric is. All right, so we've seen various densities of fabrics over time, like a very thin veil that might be used for like a boat hull could be as low as 2 ounces per square yard. I'm talking glass fiber here. And glass fiber that's very, very dense could be up to, I don't know, 24 ounces per square yard, like pretty intense, thick woven pattern. All right. So 4.3 ounce per square yard for carbon fiber, that's pretty standard. All right. That's nothing to scoff at. Some other various pieces of information here. It tells you sort of how to cure it. You get the idea. It's a data sheet. All right. Tensile strength, tensile modulus, material properties. That's of the neat resin, by the way. So there you go. All right, that's all I'm going to say about one-dimensional fabrics. This is a lecture on 2D fabrics, so I'm trying to push through that 1D portion relatively quickly. We've talked a lot about one-dimensional fabrics, so how much do you really need to know? How much more can I possibly teach you? Well, there's a lot, but for now, let's move on from 1D. And now let's talk about 2D fabric architectures. All right. And as I mentioned before, there are many types. Okay, so it's like the bi-directional weave. There's the knitted. There's stitched, etc. All right, but bi-directional weave is by far the most common. Gosh, spelling today. Spelling every day. Like I say, it's bad today, but it's literally bad every day. So literally. All right, bi-directional weaves are by far the most common. So think things like plain weave, twill, satin, etc. These bi-directional weaves, by far the most common. All right, if you're going to use a woven fabric in your life to manufacture something, like 95% probability you'll be using one of these three types: plain weave, a twill weave, or satin weave. All right, so let's take a minute, sitting right there, tell you how I became the Prince of Bel-Air. No, I'm just kidding. We're going to tell you how these bi-directional weaves are fabricated. So let's make sure that we have straight away in our head what a two-dimensional fabric would look like and what this bi-directional weave I'm sort of talking about actually looks like. So here is a unit cell of a two-dimensional fabric. So I showed the unit cell of a three-dimensional fabric, but here we need some nomenclature to make our way through the manufacturing process. All right. So here's a plain weave fabric, two-dimensional unit cell. So what you see is sort of like this over, under sort of behavior with an alternating like over, under. So this plain weave is 1 over, 1 under, 1 over, 1 under. Okay, general idea. But now you see this nomenclature here of like weft and warp. Okay, so why do we use that terminology? What does that actually mean? Well, those two terms come from the actual manufacturing process of how this fabric was made. Okay, so those two terms come from the manufacturing process. And so these guys are typically manufactured on a loom. All right. And by typically, I mean 99.999% of the time. All right. Maybe you got Grandma Hart stitching some 2D plain woven fabric in the background that's not on a loom, but, you know, very suspicious. All right. So let's take a look at this weaving process and actually what it kind of looks like. And so the manufacturing will look something like this. And I'm actually going to show a YouTube video of this just in a second, because I think the looms are an amazing feat of engineering. So very, very worthwhile, like seeing a loom in action if you get a chance. All right. So the idea here is that you have some mandrel with fibers, right? Your individual fibers, and it's feeding into this loom. And the idea is that you have many, many of these fibers that are coming together, right? And they have this patterning to them, where the fibers are coming into the machine and they're sort of like interlocked with each other. And they're hooked up to what's called this herald frame, but I've heard it more often called as the chute or the shed. And the idea here is that these fibers are all like moving into this shed and then being moved like up and down like this. And while it's being moved up and down in this fashion, another fabric toe is being pushed between this opening. Okay, so it's shuttling back and forth like this. And you see that opening here that I'm talking about, okay, being held by this shed. All right. And what happens is it's opened in this various pattern and this various configuration. And inside of this opening, a single thread is passed through that opening, let's say here, through one of these three different methods. All right, a projectile, a rapier, or an air jet. The most common is probably the rapier loom. Air jet looms are common as well, but you get the general idea. And you're building up the cloth on the back end. Here we have the woven cloth. Okay, so this is the general idea. You've got all these fibers coming in, they're moving up and down and shedding up and down, and you're passing constantly this additional toe through the opening in that fabric. And so, describing it is good, but I think a slow motion loom picture is, or loom video is worthwhile here. So this is a freaking awesome video, and I thought I would show it. And this is a rapier loom in fabrication. Now, it's making the fabric here. So we kind of see on the lower left there is the finished fabric coming off of the loom. On the upper right, you see the shed. So it's going to do this thing where it sort of like moves up and down very quickly, and it will pass the fibers through. So one thing I like about this video is it shows in slow motion the actual process of this weaving going on. All right. So you're not going to get sound with this. I do have the link in the lecture notes if you want to actually hear the sound, but I'll give you the sound right now. It's okay. That's the whole entire sound. So I'm going to play this for you and kind of walk you through, talk through it. All right. So you can kind of see the loom there was just moving up and down very quickly, and now it's playing in slow motion. And in slow motion, you can see the rapiers moving between the open layers of the fibers that are kind of making up the backbone of the longitudinal direction. All right, so again, there you see the rapiers coming in and moving the individual threads between the layers as they're sort of moving up and down. Now, what's going on here is like the black lines that you see here, each one of those black lines is connected to a fiber that's running in like the longitudinal direction. Okay, so it's all holding all these fibers, and it's causing this to shed up and down and pass the individual fibers between the opening and the shed as it goes sort of in this up and down fashion. Okay, so here we see the backside, and you see this like triangular opening here where we're going to pass through that through thread. All right. So you can see that the shed is opening all those individual layers, and that's where the rapier is passing through to pass those individual threads in sort of the cross direction. So really awesome video. I like that video a lot. It talks about and shows you the rapier moving at slow motion, and that's slowed down probably, I don't know, at least 10 times, probably more like 20 or 30 times to show the speed of that rapier. It is so fast. It's bang, 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 passing those individual layers through. Now, the reason that I show this particular video is the fibers that are running in the direction that is being lifted constantly like this, those are called the warp fibers. All right, that's like the 0 degree direction for the fabric. All right, so here, continuous toes. In weaving process. Are the warp toes. And these are often called the 0 degree toes. Now, in a fabric architecture, a woven fabric, sometimes, like let's say you have a plane weave, it can be very difficult to identify what is the warp direction and what is the weft direction, because the warp and weft direction basically look the same in a plane weave. You have no idea which one is which. All right. So you might have to have it specified, or if you have a roll of the fabric, you know that if you're unrolling the roll of fabric, which direction is warp and which direction is 90 degrees to that, which we call the weft direction. So these continuous fibers that are sort of passing through the loom and being shedded up and down like this, those are the warp toes. And then the fabrics that are being passed in between the opening and the shed, those are the weft toes. Okay. So the shuttle, or the rapier, passes one toe through open shed during process. Then repeats. All right. That pass-through toe is the weft toe, or what is, the 90-degree direction. Okay, so that's kind of how your loom works. All right. So when you see this unit cell and people are talking about warp and weft toes, or warp and weft directions, that's what they're referring to. They're referring to the way that the fabric was manufactured on the loom, and which fibers were in the warp direction, which is this continuous direction, and which ones were passed through the rapier, which is the weft direction. All right, so that's your manufacturing. All right, and you saw manufactured on that rapier loom, I'm pretty sure that was a plane weave. But here, just to remind you what these bidirectional weaves look like. This comes actually from your 429 notes, so you've kind of seen this before. A plane weave, a twill weave, and a satin weave. So here's your plane weave, your twill weave, and your satin weave, just to sort of remind you. Plane weaves, you're like standard over under. Twill weave, you have like 2 over 2 under, or you could have 4 over 4 under, or some variant of that. And then your satin weave is something like 1 over 4 under, 1 over 4 under. And they all have various benefits and drawbacks, of which we've talked about in 429. Like this guy is most drapable. And this guy is strongest. All right, so twill weave is kind of the happy Goldilocks medium right in the middle. All right, so that's the general idea. Now, I showed a data sheet for the unidirectional fabric. I also want to show a data sheet for like a woven fabric as well. And the data sheet is helpful here because it shows us some additional information that most people actually don't know. All right, so let's take a look at this data sheet, and this is for a 2D dry glass fiber plane weave. All right, so here's a data sheet for a 2D dry glass fiber plane weave. All right, so here we are. So you notice it's 4-ounce fiberglass fabric. Okay, that's misleading because if you had a whole roll of that fabric, it would not weigh 4 ounces. What they mean is it's 4 ounce per square yard, all right, which they don't say, but they should say. So here it's weight 3.5 to 4.1 ounces per square yard. This is a generally pretty thin plane weave. This is probably not quite as thin as you can get, but pretty close to as thin as you can get. All right. What you'll notice here is they tell you which yarns or which toes they use in which direction. All right, so both the warp and the fill is sometimes called the weft is sometimes called the fill. So here you see fill, also weft. All right. they're telling you which yarn specifically they're using in each one of those directions during the weaving process. So the warp is this like continuous layer again in the loom, and the fill or the weft is what's being passed through the rapier. All right, so those are the, glass fabrics that they're passing through, or the yarns that they're passing through that particular direction, and you see they're the same. So same fiber in both directions of this particular plane weave. All right, now what you'll see here is counts, ends, picks per inch. All right, this is something that needs a little bit of description. And this here is the approximate number of yarns per inch in each direction. Okay, so in this particular example, there are between 22 and 26 ends. Again, another nomenclature here, where end is just another name for warp. And pick is another name for weft. And these fabric manufacturers, they got all these like weird nomenclature. There's ends and picks and fills and warp and weft, and they basically all mean the same thing. You just got to know like what word goes with what. All right. So here between 22 and 26 end or warp toes. And we see 20, 24 weft toes per inch. Okay. So if I were to ask you, does this plain weave fabric have the same material properties in the warp direction than it has in the weft direction? What would you say? I hope the answer is no, because there are more toes in the warp direction than there are in the weft direction. Okay? This is a very common gap in people's knowledge. They see a plain weave and they say, okay, it must have the same material properties in one direction than it is in the other. So whether I lay it, 10 layers of this direction or alternate the way that I lay it up, it makes no difference. Incorrect. Okay? It has different properties in different directions, even though it's very subtle. Okay? So this is a big takeaway that I want you to have here, is that even if someone hands you a plain weave fabric, you don't necessarily know that it's the same properties in both directions. All right. So we see that here when we're looking at here, it says 24 by 22 plain weave. That means 24 toes in the warp direction, 22 toes in the weft direction. Okay. So when you're going to manufacture or create some composite in the future, when you're all working on composites, I hope, and you say, we need a plain weave for this guy, and someone hands you a plain weave and they say, here's a plain weave, it's the same in both directions, you better say, show me the data sheet, because I don't know if that's true. All right, you can't just take a plain weave and say, yes, it has the same properties in both directions. Incorrect. All right. It could be the case where it has the same number of toes in both directions, and it has generally the same properties in both directions, but you don't know that unless you know exactly how it was manufactured on that loom. All right, so I think I've beaten that guy to death. There, showing you the data sheet. Show me the data. Rawr. Show me the data sheet. Okay, that's what Donald Trump says all the time. Show me the data. Yeah, okay, no, he never says that. That's why I respect his opinion so much. Suspicious. All right. So let us continue a little bit here. That is for a dry fabric. All right, here's your data sheet for generally a dry fabric. Woven materials can also come as prepregs. And I'll say, though not as common. All right, I'd say maybe it's like 50-50 split, or leaning slightly towards getting the fabric in dry orientation. All right, so it's like approximately 50. wet and dry use. Probably leans a little bit more towards the dry use, but that's an approximate idea. So here's the data sheet. This is for an 8 harness satin weave. So that means 7 over, 1 under, 7 over, 1 under for every single fiber toe. So this is an 8 harness satin weave. Stain weave. Oh, spelling is hard. Satin weave. And this is glass epoxy. Eight harness stain weave. My new favorite type of composite, the 8 harness stain weave. All right, so again, satin weave. You see some information about, yeah, they messed up here. Carbon fiber, no, this is glass. No, glass. Okay, they messed up with their carbon fiber properties there. I think someone just forgot to change the header for this data sheet. All right, weave pattern here, 8 harness satin. You see things like the yarn description. Again, we have different yarns in different directions now. And they say yarn, but it's not a yarn, it's a tow. Yarn has twist. These don't have twist. So what the hell are they doing saying yarn? All right, warp and fill, same fiber, same fiber for both of these directions. Here's now your counts or of your ends and your picks. Okay, so how many warp fibers do I have per inch? How many weft fibers do I have per inch? Here we have 57 warp toes per inch, 54 weft toes per inch. All right, so again, not the same material properties in either direction. All right, breaking strength is different for each direction. So you're starting to see things like not going to be the same material properties in both directions. All right, so got to make sure that you see that and understand that. For prepregs, you're given things like cure temperature and resin properties, et cetera, et cetera. But I'm really trying to point out the things about the fabric that are important. Okay, so hopefully I've driven home the idea that just because you're given a plain weave, a satin weave, a twill weave, you can't assume it has the same material properties in this warp direction and the weft direction. They might be different. Though the variation is small, it could make a difference. All right. So let's look at these general in-plane properties for these 2D woven fabric architectures by comparison. All right. So show me the data. Show me the money. All right, so this is bi-directional composites. All right, so properties of typical fabric composites. So these are composites that have been made from this two-dimensional fabric that I mentioned. All right, so here's like woven glass epoxy. They didn't tell us how it was woven. They just say that it's a woven glass and epoxy composite. All right, maybe it's a plain weave, maybe it's a twill weave, maybe it's a satin weave, maybe it's knitted, who knows? All right. So here we see in the 1 and the 2 direction, which would be like the warp and the weft direction, we have like the same elastic modulus. Okay, this tells you that this particular weave was made in this symmetric fashion. So it has the same number of warp fibers as it has weft fibers. They're made out of the same material. So generally, this guy is sort of the same material properties in the 0 and the 90 direction. All right, for this particular woven fabric. That is different from this guy next door. You can see the elastic modulus here is not the same in the warp and the weft direction, all right, in the 1 or the 2 direction. Usually 1 is associated with warp and 2 is associated with weft. All right, so we don't have the same general properties in the warp and the weft direction or the 1 and the 2 direction. All right, we see that here. The warp is slightly stiffer in this case than the weft. All right, and you see that in other things here as well, like what is the Poisson's ratio in the 2 different directions? Not the same, right? So there's a couple here that generally don't have the same material properties, right? All 3 of these guys don't have the same material properties in the 0 and 90 degree directions, right? So different properties in the warp and the weft direction, as opposed to these guys, which do have the same properties in the warp and the weft direction, all right? So you got to know your fabrics. You got to know, is one direction stronger than the other, and by how much. I mean, this guy is a percentage change of, I don't know, 4%, not very much. This guy's got a percent change of, I don't know, 2 and 75 is like 3%. All right, so not that much, but you get the general idea is that they could be different. All right. When it comes to these bidirectional composites, typically manufactured since they come in dry or wet form, they can be manufactured using both dry and wet techniques. All right, so if dry, you're talking about typical dry manufacturing processes like RTM, Vardum, RIM. Your typical dry techniques. All right, so you lay your dry fabric inside of a mold, then you close the mold and you inject the resin, or you pull the resin in with vacuum, or so on and so forth. All right, so remember Vardum, vacuum assisted resin transfer molding, RTM, resin transfer molding, REM, resin injection molding. All right. Remember, they also come as pre-preg, so if wet, in pre-preg form or approximate pre-preg form, autoclave, out of autoclave, vacuum bag. All right, those are the most common if it comes in pre-preg form. So because 2D fabrics can come both dry and wet, all of the manufacturing processes that are of any interest to us would probably be possible. All right. Sometimes you'll see it as dry, sometimes you'll see it as wet, sometimes you'll see it as pre-preg, etc. All right. Last thing that I want to talk about for 2D fabrics. So far, we've really just talked about the bidirectional 2D fabrics. I want to do one last thing here on what is other 2D styles. So we kind of passed over like the stitched and woven and braided. So let's quickly talk about other 2D styles. All right. I'll say that like these are not nearly as common. All right. So braided, knitted, not nearly as common. Bidirectional weaves. All right. Though I will say that some braided structures are good for making cylindrical composites. All right. Knitted, you like never see. Braided at least has like some use. So I'll say some braided fabrics are used to create cylindrical parts. All right, so cylindrical parts being like rocket casing, fishing pole, etc. All right, so let's take a look at what this braided fabric might look like. And it's too bad that we don't have like in-person meetings, because I actually have all of these like fabrics I could have passed around. And one particularly nice example that I have is actually a dry braided fabric and then a composite that has been made from that particular fabric. So I have physical examples of these two things that I could have passed around in hand, but such is the way of the world, the current situation. All right, so here's like your dry fabric, and they call it a 2D composite because you can see it's like wound up on this like bobbin here, and it kind of has this 2D pattern. So before this opening here, so we see this opening. Before that opening was there, it kind of like was laying flat as a two-dimensional fabric. So you prop this thing open, you slide it on some mandrel or something, and then you infuse it with resin, and it becomes this sort of solid shaft from that particular braided fabric. So this exact fabric was used to make this exact shaft here over on the right hand side, and that's a common use for these braided composites, is making these shafts. I think, Will, that lacrosse stick that you had, I actually don't think that it was made from a braided shaft, but similar cheaper lacrosse sticks have probably been made with braided fabrics that look something like this. All right, last thing I want to say, and then I'll get you out of here. I realize it's 8:50. Is that knitted fabrics are rarely used, and that's mostly because of the tortuosity associated with the fiber path. Okay. And will always load, quote, across the fibers in some way. We know that loading across fibers is bad because when you load across fibers, it's stress concentration. So with these braided fabrics or these knitted fabrics, you end up with a situation that looks like this, where you have sort of like this knitted fabric. And because of the way that like the fiber travels, you see it's got like all this crazy travel path, that no matter how you load it, this way, this way, this way, this way, this way, whatever, you're always going to at some angle be loading up the fiber across the fiber. Okay, so we know that loading across the fiber generally is bad and will lead to stress concentrations and will lead to premature failure of these guys. So these knitted fabrics are very rarely used because regardless of how you load the composite that would be made from that, you're going to load across the fiber. You can't avoid it. So rarely, very rarely are these used in application for composites, especially structural composites, because like they just can't hold any load. They fail at significantly lower loads than these other types would. So generally bad. Knitted, stay away from knitted. Okay, that's it for today. I'll finish it out with three-dimensional composites on Wednesday. Thanks for coming.